My name's Andy Preston. I work for ABB, which is a big electrical engineering company for those of you who don't know us. I work for the drives division, the variable speed drives division here in the UK. We're sort of based in Manchester / Warrington as a sort of head office. We've got a distribution network throughout the country. Variable speed drive, it's a box of electronics, power electronics. There's one here, an example there. And its job is to control an electric motor, and the humble electric motor, induction motor typically, and these days typically AC induction motors. They're the most prevalent really in industry. It used to be DC many years ago. We still do DC drives and DC motors, but these days typically we're talking about AC motors and AC drive technology. And there's an AC motor in the little demo there which we'll fire up later on. And the aim of today's chat really is to talk about how probably we're missing a trick on how we can utilise variable speed drives to improve pumping, move air, move liquids, save energy, and a whole host of control and so on improvements that come along with that. Please ask any questions as they come to mind. You know, make it as interactive as you like, and hopefully we won't disturb the crew at the back too much. We'll start with a little bit of history really and what's driving the energy saving initiatives, and you've probably seen some of this information before, but it's basically the concept of the rise in electrical demand across the world. You know, we've got the developing nations in China, we've got the developing nations in India. You know, their power increase or demand for power is going up in the hundreds of %. And there was a period of time last year in China where they were commissioning a power station every week or every 2 weeks. And you know, they're burning a lot of fuel to do that. Even in Europe, where you would perhaps consider, you know, the demand to be fairly standard or even static, you know, we're still expected to grow by 30% over the next few years. So, you know, the demand for energy is growing. Everything we seem to switch on and use requires electricity. And obviously that poses the UK with a challenge with regards to generating that power. But one of the things we try and advocate from the drives department is if we control things properly and change the way we do things, we could actually get to the scenario of turning some of these power stations off, because there's a lot of waste, an enormous amount of waste used based on sort of historical use of particularly electrical motors. The effect of this increase in energy usage is this sort of debatable rise in the near surface air temperatures of the planet. I know Mr. Trump doesn't think this is for real, you know, he thinks it's a fiction. But I would challenge that significantly, especially if you look at 1940, around about here, where there was a fairly significant amount of human activity on the planet. We definitely warmed it up, and that activity soon fell. And these sort of cycles are so short that there's no way they're natural. You know, these are man-made or human-made, and as we burn more and more fossil fuels, the temperature's just going to go up, and we're already seeing the effect of that on our environment. And although the temperatures are quite small, maybe some of you have looked at these graphs before and thought half a degree of temperature rise over, you know, a couple of hundred years, that's not a big deal. But if you think about the size of the biosphere that we live on, you know, the amount of space, the amount of atmosphere, the thousands of cubic meters of air, and then think about how much energy you need to raise all of that by half a degree, then, you know, you start to get a feel for just how much energy is being stored and held in the system. So it's becoming a problem. And then if you then consider the sort of primary energy source, and when we're talking now about oil, gas, you know, wood, whatever methods we're using now to produce, which is the primary energy source, typically it has to be moved around, and then we generate electricity using that primary energy. And power stations are actually one of the worst efficient or really poorly efficient devices that we have around us. An average power station is 38% efficient. 38% efficient. So the most modern coal-fired or gas-fired power stations, the best they can do is be 40% efficient. So for every 3 train loads of coal that arrives at Drax power station, only one of them is making electricity. which is horrific if you think about, you know, the effort involved. And then we have to transmit and distribute that power. Some gets lost in the transmission lines, and then the processes and the actual industrial production at the end. So by the time we actually start turning electric motors or switching on the lights, 80% of that primary energy is gone, which is criminal really, but there it is. So for me, it's really important to save as much as we can. I know we talk endlessly about turning mobile phone chargers off and that kind of thing. You know, there's 70 million people in the UK now, and if everyone saved 1 watt, that's a couple of power stations. So that's your charger plugged in, you know, your telly's on standby, the whole thing. And for every kilowatt you save here, it has the effect of, you know, sort of not using the primary energy source by a factor of 5. So it really does matter. So the more we can do, the better. Which is why, from the drive's perspective, we spend our lives sort of focusing on energy and the amount of energy that drive can save. Drives, I guess, you may think of them typically as something that you would employ to bring some control to the system. You know, make something work faster or slower, or improve the process quality of something. You know, that's what they do. They've been doing that for years, productivity improvements. But energy is also a big way of using variable speed drives, and I don't think they're being used enough. And the reason we focus on the motor is because of figures like this. 65% of the energy being, if you like, transmitted and put into most of the energy industrial processes in the UK, 65% of that energy is being used to just rotate electric motors. You know, way over half. And I challenge, I suspect that number's even greater. 95% of those motors are the wrong size. They're just the wrong size. And if you think about sort of standard engineering processes which require each and every one of us to add a little bit, 10% here, 10% there, I'll add 10% contingency. Even if you designed a perfect system and you came to a conclusion that at the end of the day you needed 33 kilowatts of motive power, and you open the catalogue of any motor manufacturer in the world, you can't buy a 33 kilowatt motor. You can buy a 37. So even with the best intentions, you will end up, because of catalogue capabilities and what's available out there, systems are oversized. They're just oversized. So that kind of poses a problem. That leaves you with an issue where the systems are too big for the job, and we need to sort of instigate some kind of control. How do we work that out? And how can we use drives to sort of solve that problem? So I'll pose you a question, and it's a relatively simple one. We're driving down the road, and there's a speed limit sign, 30 miles an hour, and the vehicle we're travelling in is doing 40 miles an hour. And I know the camera's pointing the other way, so don't pick me up on that. I've had that one this morning. There's two possible ways of dealing with this sort of scenario. You can either take your foot off the accelerator and slow down, or you can keep your foot on the accelerator and apply the brake. Or you could press the accelerator even harder and go full speed and apply the brake really, really hard. So what's the answer to the puzzle? Hopefully. Unless you make a pack and then you can do the whatever. Hopefully you're going to choose A, yeah? You're going to slow down. You're going to take your foot off the motive force and you're going to slow down. The car will lose speed. But the problem is, in industry, they don't do that. In industry, typically, we apply our foot on the accelerator full tilt and apply the brakes. We connect variable electric motors to the grid, direct online, and run them at 50 hertz all the time. Full speed, foot to the floor. And then, in the pump system or the air duct system or whatever it is connected to the driven load, we apply some mechanical constriction. So we apply the brakes. Okay? And this particular pump system is being pretty heavily constricted. You can see that the valve is 50% closed or 50% open, whichever way you want to look at it. That's a serious oversizing problem. And this is at a car plant for a very prestigious car manufacturer who's had this plant installed, and during the commissioning process, to make the process work, the solution was to crank the valve shut by 50%. So apart from the fact that he's probably bought a load of kit which is too big, he's also wasting a significant amount of energy. And I don't know whether you'd ever considered that scenario as being foot hard on the accelerator and I'll apply the brake to take control, which you naturally just would not think to do in real life. But it's so commonplace in the workplace that you probably don't even notice it. You probably walk past valves, dampers, you probably install them thinking, that's perhaps the way to play it. And what we need to look at then is what that means in terms of energy wastage. And when you're actually driving a load like a fan or a pump, and you guys probably know this better than I, the system curve, the load versus speed curve of a pump or a fan is quadratic. So it follows a quadratic law, not a linear law, a quadratic law. So power is proportional to the cube of the speed. So at 100% power, we're going to draw nominal load, whatever that might be. But if we slow this pump down or fan down by 20%, that particular system will draw half the power it did before, 50% of the power. Now, in terms of frequency, I guess you're all maybe used to the idea of an electric motor going at 50 hertz. So that 20% reduction in speed is actually, you're moving the frequency now to 40 hertz, which is not really a lot, if you think about it. And by just doing that, that system will consume half the energy it did before. Okay, so whilst on the one hand you perhaps think of variable speed drives as a complicated piece of electronics for process control of my super duper process or servo, or like the robot, the Yumi robot downstairs, some precision control. Variable speed drives are also very, very good at just fixing a speed at a different value, a value that is not the mains frequency, and stay there. There's nothing wrong with that. Driver will happily operate that motor at 40 hertz for the rest of its life and not worry about it. But meanwhile, although you've had to pay for the drive, you're saving 50% of the energy bill. And whilst energy is never going to go down again, that's only going to pay money into your pocket. The car manufacturer from the previous slide was operating at a 50% flow rate. So if we open that valve and slow the motor down instead, he would save 80% plus on his energy bill. And there was actually, I think, 17 pumps of exactly the same setup, and they were all about 37 kilowatts. So that's half, 80% of 37 kilowatts times 17. So it was a fairly easy drive sell, to be honest, but but they're everywhere. And a brand new plant will be set like that because someone will have purchased the install on a price, not thinking about the ongoing cost of ownership. And if we look at it in another way, just so we're not knocking the mechanical situation, because the mechanical restrictor does in fact save energy. So there's our system curve again. And if we look at the energy being used by the system when it's using the mechanical constriction, it does save energy. The affinity curves say less work done equals energy saved. So by restricting the flow, you do actually make a saving. So, as a technique, it has some merit. But if you then if you compare that to what the drive would do in that same scenario, you end up realizing that you save the difference of that. The drive will consume energy, so the green line is not on top of the black, but the difference compared to the restriction is quite significant. And we tend to refer to that as the rugby ball in the office. Don't forget about the rugby ball. Save the rugby ball. And we've taken this concept to various people. We've got an energy appraisal team in ABB, and we work with our partners, and they're able to do energy audits. They're able to loan you a drive if you're not convinced and do before and after measurements. There's all sorts of ways of looking at these problems. But McDonald's were a group of people who worked with us, and they were prepared to reduce the speed of their cooker hood fans by a small amount. They didn't want to make the kitchen, get full of gases and, smoke and what have you. But they wanted to have a go at saving energy. So they went for a very small speed reduction on their fans and ended up saving 20% energy. And we rolled this out across, I think, pretty much all of the McDonald's restaurants now in the UK now have an ABB drive on the roof controlling the cooker hoods. And McDonald's are happy about that, because straight to the bottom line, you end up with, profit, or money not spent, if you like.
Is there something that sits in the line then, between the power and the motor?
Exactly that, yeah. If you've got a direct online motor, you connect that directly to the three-phase, usually with some kind of a starter. You could even leave the starter in place, basically cut into that cable, and the drive goes in that gap. The only thing to worry about is really the type of cable to the motor. But because we use steel wire armour so much in the UK now, I would expect the supply cable to already be suitable, because it'll already be steel wire armour, most likely, or SY, something like that.
Where's the point at which the speed and the cooling contradict?
On the motor, a good question. Now, it depends on the application. We're obviously talking about quadratic loads, as we call them here. These are loads that follow this quadratic curve. And what you find is, as you slow them down, because they're using less energy, you instinctively therefore need less cooling. So it kind of pays off. If it was a constant torque load, like an extruder, then the relationship is more linear. So there is a point where you have to be careful, and that'll be application dependent. But yeah, you have to be cognizant of the cooling, absolutely. But on a quadratic curve, fan or a pump, as you slow the motor down, the fan on the back of the motor is having to do less cooling, because the motor's having to work less hard. So it usually pays off quite well. So we can use drives to sort of save energy just by slowing things down, because the pump systems have been oversized, and we've got this ability to just fix the speed. Don't think that the drive has to vary, but of course it works better if you vary it. That's kind of the whole point. And what McDonald's, in fairness, are now saying to us is, well, you've done that, that's fantastic. Can we get more out of the system? And we could go round and program the drives to run at slightly slower speeds and see at what point the kitchen fills with smoke, and that would be a bit kind of perhaps a bit Stone Age attempt. So the better way to do it is to measure something. Take some kind of a measurement, either on air turbidity or air quality perhaps. Or even put an anemometer in the airflow, something like that. They've chosen actually to measure the current going to the fryers. So when the fryers are being worked hard, the fans blow a lot, and when the fryers are not working so hard, the fans can slow down. So that's where they've closed the loop on that, and we're currently kind of working through that as a process. So measuring something and getting the drive to actually vary obviously pays off again. But don't forget about this fixed thing, because it's a slightly easier and less risky thing to do. Now, this business of closing the loop, we have to employ a technique called PID control. So this is proportional, integral and derivative control. It's a control algorithm method. And you can buy PID controllers off the shelf, but these days most variable speed drives, they've got them built in. You bought the drive, they're already there. All you have to do is provide the drive with some kind of measured quantity, temperature, pressure, flow, whatever. If you can measure it, we can control it. And this is a very modern vehicle for those of us who drive Astons. Let's just have a think about PID control. I mean, the PID controllers are around us all the time. It's nothing really to be frightened of. And so if you think that a PID control is something where you give the system a reference point, there's a measured value which it compares against, and then something happens to make those two equal. How many PID controllers can you see or can think of in a sort of a reasonably good quality vehicle that you might be driving today? Any ideas?
Cruise control.
Cruise control is perfect, absolutely perfect. Speed set point, speed feedback, and the cruise controller sort of uses PID control to bring you up to the speed that you want to operate at. Good one. The power steering pump, it'll be to do with the harder you push, the more help you get. Yeah.
Temperature control and the
Climate control is another good one. You're going to set 20 degrees or whatever in the cabin, and it's measured, and the fan rotates or at whatever speed to make that happen. Good. Good.
The driver.
The driver,
Yeah.
absolutely.
They're working out the
The driver is a PID controller. You may question the accuracy of it sometimes. I've got 30, but I'm going to do 40. That's kind of not how it should work. But yes, the driver's a PID controller. You're the guy noticing the error and doing something to correct that error. Apply your foot on the brake or the accelerator. Good. So there's quite a lot, and you could go with automatic cruise control. Adaptive cruise. The distance measurement as well. So you've got a PID nested within a PID, distance followed by speed and so on. So they're everywhere, and we contain the mathematics. The control mathematics are in pretty much every drive. And you just have to give us a signal. We can measure unburned oxygen in a furnace and control the air being blown in to maximise the burn characteristics of a furnace. All sorts of things can be controlled when you can measure it. And so the drive contains this PID control, and by tuning the PID control, we can get the correct response to a change in set point. We can get a nice, clean sort of, approach point, nice snappy control, so that variable is held in control. And that will, of course, vary the speed of the motor. And we're going to gain more and more savings as we do that. Another thing to remember over the years is that not all drives are the same. Not all the technology is the same out there. It's important to kind of realise that. ABB have been making drives for 30 plus years, and about 1984 or 86, we launched a motor control platform called DTC. And at the time, it was the holy grail of variable speed drives. There was one thing that AC drives could not do on an AC motor, and that was to produce full torque at 0 speed. So in other words, a motor with a shaft with a load on the end, like on a crane or an elevator, to hold that motor still is really, really, really hard on AC. We've been doing it for years with DC, but with AC, that was the holy grail. And the only way AC motors were going to take the place of DC motors in industry was if that was done. So DTC cracked it first. That put ABB on top of the drives pile, and we've stayed number one ever since. But DTC also is an efficient way of controlling the motor. Look at this motor here, hottest point 22.7 degrees C. We take the DTC controller away and we fit it with an old ABB drive which used some quite ancient motor control switching techniques, and within 7 minutes that motor's temperature had doubled. So it's not just about having a drive, it's about having a decent one as well to make sure the motor control algorithm's good. Otherwise you'll just waste energy a different way. So now we've got this drive. Now what are we going to apply it to? Where are the best wins? Where are the applications we can win quickest? And the easiest wins by a mile are anything with a centrifugal fan on it. Mostly because you've got the quadratic curve in your favour, and you've really got no major difficulties with the system. You're blowing air into a duct or something which is relatively easy, and therefore you're not too many constraints for design. And we can put a PID loop around that on pressure or flow, or it could be this room, it could be temperature of the room, so that control how much flow. And we can get some massive savings. And we've done many applications around the country where people have invested in VSDs to save money. The second most prevalent application in industry is pumps, so fans and pumps, and as luck would have it, they're both quadratic. They both have a quadratic load. Pumps a little bit more challenging because of the head issue. So as you're pumping liquid uphill, obviously it requires energy to do that. And the higher the head, the more energy it needs. So the system curve won't necessarily be a perfect quadratic curve. It might be flattened. So the energy saving potential goes down, but it's still there, And again, we can employ a closed-loop PID system to control flow or whatever the variable is you've got available to you. But maybe an application that you hadn't considered is hydraulic power packs. I know we're in the kind of hydraulics discussion today, and a lot of you are with hydraulics. Now, this is a system where an electric motor drives oil, and the oil itself is the motive force. So this machine here, it's not a very good photograph, is a machine that makes plant pots. So you pump the oil up to pressure, and that oil is then used to pound the plant pots out. You know, I'm guessing you know the types of machines we're on about. Now, the problem with these machines is they have a motor with a pump. The liquid gets pumped up to pressure, and there's a burst valve. The valve bursts open, and when the valve opens, the motor carries on going, but the liquid is pumped around a sort of secondary circuit whilst it's not being required. And then when the pressure in the system falls, the burst valve closes and the system comes back online. So if you look at the load on the motor, it's sort of going, it's kind of a square wave. You know, it's on load, then it's off load, and it's on load, and then it's off load. And the offload times are dependent on how much energy the machine is using, I guess. But if you actually look at the pressure, it's a sawtooth. It goes up, and then it drops, and then it goes up, and then it drops. So the pressure's rubbish as well, actually. From a controls perspective, it's all over the place. The machine probably isn't working as well as it could because of that. So if we take control of these motors, put a pressure sensor into the system, and then tell the drive to retain 6 bar or 5 bar or whatever it is you need, everything runs without and all of that clatter and bang. And one of the things to remember about an electric motor is even when the system's running off-load, an electric motor will consume 30% of its rated power just magnetising the motor. So you've still got that as a standing load in the background. And if you've got long periods of offload, you know, you've got enormous amounts of energy saving potential. So we've upgraded many hydraulic power packs over the years to take control of this PID loop. We did one at Jaguar Land Rover. Sorry, it wasn't a hydro pack. It was an airline for the robots. So we monitored the air at the robot. It needed 6 bar. So straight away you're getting a better measurement. You know, we were able to control the air compressors much better back at the other end of the pipe to just deliver just what was needed, rather than overpressure and underpressure systems. Then you blow leaks because the pressure's doing this, and there's all sorts of knock-on effects. One of the other classics in industry is duty standby. You know, your mechanical guy or your maintenance guy or the guy running the plant will want duty standby, because what he wants is backup. He wants to know that he's got some pumps or fans not being used, so if this one fails, he can use that one. So he's got his duty standby system ready to go. And what we find in reality is that unless it's a really good place, the maintenance of these standby systems is not happening. So this one fails, you bring in the standby, it's been sat on its bearings for 6 months, and the bearings collapse, or it's not been greased, so your standby fails just at the point when you need it. And that happens, smiles, all too often. So one of the things we're trying to promote, and it's not perfect for every application, by the way, is to say, well, let's run all of these pumps at the same time, or all these fans. That actually gives us the opportunity to reduce the speed of all of them still further, because now we've got twice as much pumping capability in this scenario as we did there, so we can go lower with the speed, so your savings are greater. And if that one did fail, because the drive's in PID control, it would just raise the speed of the remaining 5 ever so slightly and just take up the slack. You can isolate that one, fix it, put it back into system. You've still got redundancy. You just haven't got idle kit, and you're making use of them to save you some energy as you go. And we did the Valhalla ride in Blackpool and pumped the water around the water flume this way and saved them quite a significant amount of money as well. But we get a lot of scepticism. We get, well, why doesn't everyone do this? This is a bit of a no-brainer. And we end up having to like convince people, if you like, of what it is. So we have a nice little mobile demo rig. So apologies for the noise, guys, but we're gonna do a demo. The process is represented by the balloon. We've got a drive, we've got a motor, and we've got a fan, and we've got a damper. So it's kind of typical of many, many systems. So I'm going to start up, and for those of you who can see the screen there, the drive's outputting 50 hertz. So that's simulating mains. And with the damper fully open, you can hear there's way too much air. So the balloon, crazy. So we're going to employ the mechanical damper and take control mechanically. Okay. You see there's some turbulence, the balloon's struggling a bit, but it's under control. Bit of reduction in volume. Now, there's a little watt meter here. It's like a B&Q watt meter. I don't know if you can read that, but it's reading 236 watts, 236 watts with the system fully open. Now I said when you close the valve you'd get some energy saving, so let's close the valve. The meter's now reading 146, so it has actually saved some energy, and so as a method, historically, it's not a bad method. I'm just saying there's better ways of doing it. And if we now put this in variable speed, so we're going to slow the motor down so it's not going 50 hertz, and we're going to open the valve so it's effectively the valve is out of the way. So you get the same balloon height, which is the same process throughput, a lot less noise. You guys can hear me now. 41 watts. So 246 to 41 for the same process. And I'm talking about closing power stations down if this was more adopted. DOL, as far as I'm concerned, should be outlawed. And actually the rules are actually moving towards that. You're probably already aware that in Europe you're not allowed to run IE2 motors without variable speed drives, and that'll only get more stringent as we go forward. So there's a nice practical example of how it really, really works. And that's because of this cube law.
Are you going to show us the other curve that relates the cost of the drive?
Sure, yeah. Yeah, I haven't got any curves, but it's a good question. Clearly, we're purchasing a piece of power electronics. And clearly, that is going to be more expensive than a direct online contactor. Absolutely. And it could be, depending on the type of technology you buy, 5 to 10 times more. So you kind of look at that and go, hold on a minute, that's crazy. I'm multiplying my project cost by 5. On a fan and pump system, we're typically seeing 6-month paybacks and less with present energy prices. So 6 months after you bought the drive, it's making you money. And that's kind of the important thing to remember. So once the payback time has kind of come to that end, and it may be a year, depending on the system, it might not have a perfect quadratic curve. Obviously, that's very, very theoretical. It might take a year, it might take 14 months. But after that point in time, you're earning money. It's now an investment. Yeah? And it's quite typical to nowadays. When electricity was 2 pence a kilowatt hour, 4 to 5 year paybacks were quite common. And some people were going, hold on a minute, company policy is 2 years. Now with 8 to 10 pence per kilowatt hour, paybacks are well under the 1 year, regularly well under the 1 year. And the other thing to remember as well, when it comes to motor purchasing, a motor will consume its price in electricity, its purchase price in electricity, in about 30 days if it's running 24/7. 30 days. So when you're purchasing guys shaving pence because he doesn't want to buy an IE3 motor, he wants to buy an IE2, 1 month after he's made that choice, he's kind of made a bad choice. Yeah, and motors will last 20 years, so that's 20 years of loss. So hopefully that answers your question. I would expect less than 2 years is almost every time, less than 1 year, more than half.
And in the applications you've talked about airflow.
Yeah.
in hydraulic systems, we have variable displacement pumps
Yes,
that sort of do.
similar, yeah, one of the
Similar
chaps
idea.
asked about that.
But then when we put, so would the argument be, because variable displacement pumps are very expensive,
Yes,
so would you then do away with the pump and put a fixed displacement pump on?
yes,
So then we have a much bigger capital cost.
and then and with the drive at the same time.
With the
And
drive at the same time.
the guy this morning asked the question. Off my head, I haven't got that exact comparison, and that's probably worth doing.
Because
I think that's a good one.
Swash plate pumps are very expensive,
Yes,
but very effective.
yes,
And the other question I'm always concerned about with direct drives is the speed of response, because not of the drive, because the drive itself
Yeah,
can
yeah.
move very quickly,
yeah,
but you've got the mechanical mass
the mechanical mass.
that you need to accelerate very quickly.
Yes.
Typically, 15, 20 milliseconds for a swash pump, for a really good swash pump under servo control.
Yeah, yeah.
And I mean, does that meet that sort of?
Well, you're
big
right.
motor?
The drive would, and if you needed that response time, you'd need enough current and torque. So you'd have to look at that cost balance. You know, maybe you'd be getting a bigger motor to give you the push.
Yeah.
And you'd have to look at that balance. And it's something we probably need to look more at. But
It becomes more of a capital purchase
absolutely,
rather than a retrofit.
yes, at the beginning of the design process.
Yes.
But it's definitely something we should be looking at. And we could do some checking if there's an opportunity to do that. But yeah, choices of design. Not just retrofit. Yeah, it'd be better if people were doing it from the beginning, to your point, getting it right. Which kind of brings me to the regs, I guess, because the regulations are changing. The regulations are pushing manufacturers like ABB to generate more efficient equipment. And up to date, the regulations have really been talking about make your component more efficient, you know, make it as efficient as you possibly can, make the motors a bit more efficient, make the drives a bit more efficient, make the pumps more efficient, make the fans more efficient. But I think there's a realization now that that's not enough. You really should be thinking about how those systems are put together and the choices you make whilst you put those systems together to the point you're making. Now, EU MEPS has been talking about motor efficiencies for a while, but there's a new standard on the block now, this EN 50598, which is talking about system efficiencies. And you're probably aware that motors have been getting gradually more efficient, IE1, IE2, IE3, and so on. Up to IE4 we are now with induction motors, and there's a proposal for IE5, this ultra premium efficiency. But really, it's getting to the point where your humble induction motor, you can't make it any more efficient. I'm guessing you guys are seeing that with your pump designs and your hydraulic designs. If you look at the curves, you know, the efficiencies of an IE4 motor at 300 odd kilowatts is in the 90%, 95%. But an IE4 motor at 0.12 kilowatts is only 70%. You know, these are the allowed numbers because there's an acceptance that you can't make a motor efficient when it's little. And the reason for that is to make it more efficient, you need bigger copper components, so there's less resistance, so there's less heat given off, and so on. Yeah, but you can't do that in the envelope of a standard induction motor frame. So ABB have been looking at that, and we've come up with a new idea because the induction motor's design sort of concept has kind of come to an end, really. And so we've come up with this idea called synchronous reluctance motor. Now, if you consider an induction motor, you generate a field in the stator which induces a second magnet in the rotor. Now you've got two magnets, and just like, you know, playing around as kids with bar magnets, north, south, and so on. Once you've got two magnets, you've got forces. And in the case of an induction motor, the magnets attract, and as we rotate the field, we pull the rotor around. But we've induced a second magnet. And in an induction motor, the magnet that you induce gives off a lot of heat, and therefore losses. And probably the biggest contributor to the losses in an induction motor is the rotor itself. It gets warm. So the bearings get warm, the greasing intervals have to be tailored to all of that. I need a fan on the back end to keep it cool, etc. With the advent of drives, we can create some quite complicated field structures within motors. We control permanent magnet motors, we can control AC brushless DC motors, and some of them have trapezoidal waveforms. There's a lot of complexity. So we've employed that ability of the drive to create a complicated field by generating 4 field poles, and by using reluctance, which is the guiding of magnetism, not the guiding of electricity. We've generated low reluctance paths in the rotor design and high reluctance paths through the air gaps here, which guides this field through the rotor. Now the rotor doesn't magnetise, it just lets the magnetism flow. So you end up with sort of magnetic elastic bands connecting the rotor to the stator. Now if we move that whole field round, the rotor follows, it's synchronous, and from our perspective that's great because we got really good speed control, about 0.1% without any feedback. But more importantly, we've got a rotor which is not magnetic and therefore doesn't give off any losses. So the I²R losses of the rotor are lost, and the synchronous reluctance motor ends up with 40% less losses than the equivalent induction motor. And we can build that motor, because it's the same basic design, into a standard induction motor frame. And standard induction motor menders can mend them, and winding shops can handle them, because it's just an induction motor. Or we've taken that same design and squashed it into the smallest possible mechanical package, and in some cases that can be 2 frames smaller than the equivalent induction motor. So you end up with a smaller motor for the same power. So if you've got a machine that is space critical, that's a big deal. Also, because we're not magnetising the rotor, I've mentioned already it runs cooler. It's lighter by up to 40 to 50%, and it's quieter by up to 9 to 10 dB. All because you're not bothering to magnetise the rotor. So it's quite a significant change. So we're hoping that you're going to use more drives with motors, so why not pick a SynRM motor, because you might as well get the benefit of both worlds. And if you compare it to permanent magnet, which is the new kid on the block for efficiency, permanent magnet motors are 3 times the price of an induction motor because of the rare earth magnets. Whereas the SynRM motor is maybe 1 to 2%, 1 to 5% more expensive depending on the frame. So it's in the ballpark, and you've got similar technology, same frame sizes. Permanent magnet are all over the place because they're designed for machine tools. So you won't get them in standard induction shapes. So we're hoping that SynRM will be the new motor design on the block. EN 50598 is coming along to help us, if you like, because the regulations are saying we need an IE classification for motors. And we know about those, I guess, 1, 2, 3, 4, 5. There's a new classification for variable speed drives for the drive module. And ABB have classified the drives against the new standards. IE2 is the best a drive can be today, 98%. So we comply there. And there's a new classification, IES, for the system, drive plus motor. And because we make both, we're able to guarantee package efficiencies for our drive motor package with a certificate straight off the bat. People who don't make both are going to struggle with this 50598 reg as it comes along. And on top of that, because we've got a variable speed system, you're used to choosing best efficiency points for pumps and fans and so on. We're quite used to looking for efficiency islands in our drive motor combinations. If you run motors and check their input power versus output, in the system measurements, you find there are islands of high efficiency. And quite typically, those islands are higher up than 50 hertz, rather annoyingly. So we're not gaining benefit there. So if you were choosing a pump or a fan with your 50 hertz limit, you end up with a set of choices, which may be limited on the system curves you've got. But if you can extend the speed range and start to say, well, let's choose some fans, pumps, or hydraulic systems which naturally are designed to operate at higher speeds, and they fit within the envelope of the drive motor package efficiency island, Now you're starting to put systems together which are the best efficiency systems. And now, you know, the Fred in the shed in China who's knocking out pumps and fans at half the price we are, he can't do this now because he's not putting the system together. And once you start putting the system together, you've got a new sales advantage. You've got a new approach to the market. Sell the system as opposed to the component, and use the drives for, you know, in this case, getting the system efficiency correct. So, because we're running out of time, sorry, summary. Variable speed, massive energy savers, really, really good at process control, but you hook that up with the synchronous reluctance motor and the ability to choose your best efficiency point based on the best optimal speed for that system. You know, it could be 53 hertz or 47 hertz or 32 or 96. I don't care. We can do them all. That drive there will happily create an output up to 600 hertz if the motor can handle it. So, this, you know, whatever speed you want, we can make happen. And then we can tune the pump system to give you the best efficiency point for the job in hand, rather than just picking components out of a catalogue which are naturally probably not going to be necessarily the most optimal. And using this efficiency island concept, we can, you know, start to squeeze tens of percent or depending on the system that we're operating on. So drives of the future. Start buying drives. That's it from me. Any questions? No? Blown away. Thanks for the interaction earlier on anyway. Thanks very much. That's me done, and enjoy the rest of your day.
Thank you.
Very good.
Thank you.